Okay, in this video we will continue our topic of exponential smoothing. Recall in the last video we looked at the derivation of the exponential smoothing formula. We saw why it is called exponential. It has an exponential pattern about it. We also looked closely at that parameter alpha and how that thing is so important because it ranges from 0 to 1, and that parameter, we call it a tuning parameter, allows us to be able to set the weighting in a way that's most appropriate for a given data set. Recall that one of the drawbacks, one of the weaknesses of the MA smoother when using it for prediction is the fact that it assumes that all previous values have an equal amount of weight on future values, and that's not that realistic in many cases, and that's why exponential smoothing is an improvement over MA smoothing when using that as a prediction tool. With that, let's move over to R and we will look at some code. So we're going to look at two examples, and our first example is West Texas crude. Remember WT crude 2020. So that's what we have here, and we're going to only consider 36 months, that is 3 years of data from the WT crude 2020 data set. So what we'll do is we will window a certain amount off, WT crude 2020, comma, start equals C 2018, comma 1. That says to go to January of 2018 and go through 2020. So we're going to have 3 years of data, 36 months worth. And what we're going to do next is we're going to turn that into a numeric, because if we were to do a class command on WTC36, you will see that it says TS, meaning time series. And we're going to need to turn that to a numeric only because exponential.smooth.wge, you can see that in the line below, the TSWGE function requires a numeric. That's the only reason that we're doing that. So let me run that little piece right there, get that done. And then I would like to focus on detail on this syntax. So in TSWGE, if you want to get the exponential smoothing forecast, we said in the last video, don't do it by hand. We saw that that's going to get very tedious very quickly, lots of calculations. The good news is this command will do it easily for you. All you do is exp.smooth.wge, then the first argument is the data set. Remember that data set needs to be a numeric. The second argument is the alpha level, and remember this alpha parameter ranges from 0 to 1 as we mentioned earlier, and we're going to give it a value of 0.4. That's a common value. Remember, if we said nothing at all, the TSWGE would try to come up with an estimate of alpha on its own that minimizes the least squares error of the forecast. So that's another option for you. And then n dot ahead equals 4. That's just simply saying how many forecasts we want in the future. Now remember that these forecasts are going to be one step ahead forecasts, but we want 4 of those. And that's what this command will do. Let's run that and see what we get. So here's a plot. It overlays the forecasts on top of the actual. Now the actual here, it's not labeled very well, but I can tell you what that is. The actual would be the dark line and the dots. That's actual. The predicted would be the other line. That's the lighter line that has triangles in it. And notice how it does a really good job. It's a little late in finding this dip, but it does go down about the right amount. It comes along pretty well. Again, it dips a little bit late, and then at the end it comes along here. And I want you to take a look at this. Remember, the last data value is this. The actual data value is this dot right here, the dark dot. The triangle below it is the exponentially smoothed forecast value, and then after that, there are no dots because there's no actual data after that value. The exponential smoothing forecast is here. It kind of increases, and then notice what happens from then on out. It stays at that level. So that's one of the features, one of the properties of exponential smoothing forecasts is that they're going to flatten out, and they're going to flatten out quickly. That is, they're going to flatten out immediately after that n plus 1, whatever the n plus 1 forecast value is, that's this triangle right here. Every value after that is assumed to be that value. Now, why is that? That's weird. And speaking of unrealistic, well, that's because of an assumption that exponential smoothing assumes. And that assumption is that there is no trend and no cycle in the data set. Now, that you might say to yourself, well, that doesn't sound very realistic. And in some cases, you're right. But in other cases, there's not a trend and there's not a cycle. And in cases like that, this may be the best that the forecast can do. And it's the most conservative estimate. But that is your first look at exponentially smoothed forecasts. And again, focus on the fact that it did a great job throughout the data set. But then at the end, it gives one value that's going to be different from the last the last forecast, but then it's going to flatten out. Whoops, went too far to the left. Okay, now the other thing I wanted you to see is this. What would it have looked like if we had used MA smoother with an order of 5? So let's run that. Looks a whole lot like the last picture. Right. Now, notice that at the front here, there's some missing values. Why are there missing values? Well, remember that for the MA smoother, you've got these end effects where if it's a smoother of 5, there's nothing that can be calculated for the data value 1, 2, 3, and 4. It can't even start until data value 5. So that's why that is blank at the start here. All right, well, and again, hey, it does a pretty good job. I don't think that it necessarily tracks the dips as well. It's definitely late, and when it is, it's not as sharp. But it's very similar to exponential smoothing. But notice the end. At the end, it does a little bit. It's different. It's not flat, and it tries to make some forecasts about some change. So it is, well, why is that the case? Well, remember, it's using averages of the last 5 data points, and it's just moving over sequentially in time. But I will point out, maybe this will be more clear in the next example, but this thing is headed towards the average. It just takes a while. It takes a while for it to flatten out, where the exponential smoothing forecasts get there immediately. So let's go to example 2 now. This will be DFW.year. Remember that that's the DFW annual average temperatures. And we need to turn it again to the numeric because the exponential smooth.wge function needs that to be true. Now in this case, looks like we're going to have an alpha of 0.2, and we're going to look at 10 forecasts ahead. So let's look at that. And here's a plot of that. Again, the actual would be the dark solid lines and the dark points. That's actual. And the exponentially smooth forecast, one step ahead, will be the lighter line with triangles. And you can see that it's smoother. And one of the reasons that it is it's trying to predict the mean. It's not, so it's not going to be as volatile. It's not going to have the erratic extremes that the actual data possesses. And again, at the very, so it does a good job. It definitely travels through the points in a very suitable fashion. It just doesn't follow the extremes as much. And then at the very end, what happens? Again, let's focus on that very last data value. That's this solid line right here. Looks like the exponentially smooth forecast is right up above it. And then the next forecasted value is a little bit below it, and then it flattens out there for the next 9 values, which we know is one of the features of exponential smoothing. Let's look at what would have happened if we did an MA7, which is something that was given in an earlier example in the text and a video as well. And you're going to, when you look at it, you're going to say that it really looks a whole lot like that plot that you see in front of you now for exponential smoothing forecast, but it won't have the flat forecast at the end. Let's take a look. And again, it does a good job. Notice you see the end effects here. It does a good job of traveling through the points, not including the extreme. But at the end, you can see that it, instead of flattening out, it sort of tries to mimic this sinusoidal behavior. But if you would follow that out further, and you can also see some evidence of it even now, it's beginning to flatten out. So it doesn't do that forever. Again, it's just not as fast as the exponential smoothing forecast, which happens immediately after that first forecast. So this is what I had for the exponential smoothing forecast, the syntax for it. You can see that, hey, that's a lot easier than calculating it by hand, that's for sure, and very easy to run. And I could see how a person could say, yeah, but that's just not very, that's disappointing because I'm not expecting flat forecasts. And you're right. We're going to learn about a model called an ARMA 01 or an ARIMA 010 in a couple of chapters, and it turns out that the simple exponential smoothing algorithm is the very same thing as an ARIMA 010, and oftentimes that is the best estimate that you can give for a particular type of data. Not all, but for some data sets, they are most appropriately modeled by an ARIMA 010, which is equivalent to this exponential smoothing algorithm and formula, which is quite interesting. Now, one last thing before we stop here. Recall that one of the assumptions for exponential smoothing is that a data set has no trend and no cyclic behavior. And that's not going to happen in a lot of cases. A lot of times there is a trend and or cyclic behavior. So what do you do in a case like that? Well, not exponential smoothing. In a case like that, we extend to Holt-Winters algorithm, and that will be next.